yesterday, we did mostly one loop calculation that you already knew. Okay, computed the one loop contribution that we computed in 1947 or 48 on the one. And also we computed the normalized one loop double polarization. But these are calculations that we already did. Now we will put things together at the two loop level. And we will see perhaps some techniques that you less know. That I will first recall the basic equations we found yesterday. So we have that the anomaly given by this one loop diagram could be expressed as the following integral over x. I also write the integral over y also here. It is only 1. To recall the fact that the denominator here, if you don't keep the q square, if you don't put q square equal to 0, which is the case when you compute anomaly, okay, because you compute f2 at q square equal to 0, you have here some terms that depend on q square, and they also depend on y. So this is just to recall this fact. But here we put q square equal to 0, so this integral is simply 1. Okay? You also have here, if you keep the mass of the photon, the term proportional to its mass. So this simply gave this result. Okay? We have also shown that the vacuum polarization was given like this. Times the function which we have normalized, which was like this. Simple equations with the right term yesterday. And we have also shown that the replacement of the free boson propagator in this diagram by the vacuum polarization, you get anomaly coming from the two-loop diagram from anomaly coming from the one loop. Put it done. Okay. If you replace so this by I j mu rho by normalized k square over k square. Remember this? Okay. So this is what we are going to do now. And I also wrote yesterday an equation which was the following. Was in fact this. The corresponding final diagram. Plus m dividing. I think basically we were there yesterday, and I said that if you put here the expression of this integral, you have quite complicated k-square dependence that you cannot easily compute just like this. So there is a trick, and the trick is that in fact your normalized vacuum polarization will be written as a dispersion relation. Remember this? I also showed it yesterday. So it was the following equation. Where you see that doing this, you can separate the dependence of this integral in the k-square dependence, which now is more simple. Okay? And you see that if you put this equation here instead of pi, you have a cancellation between the k-square here and this one. And at the end, you have this, which is nothing but propagator of a photon with a mass squared t. Okay? So if I put it, inside, I simply have this, the minus sign is for equivalent to this, and I find simply pi imaginary part and the integral I said that when you keep the mass, the only change in this equation, when you keep the mass of the photon, is that you add a term here, which is proportional to this mass. So, in fact, since this is the mass we can rewrite this equation as inject this inside this, get well, I should write to the left hand side, we get AL or I follow here down the integration instead of t
times this integral as n squared plus n squared square 1 minus x. Okay. This is simply this result from the common theory. Okay. Now, this is nothing but if I take this and put it here, the dispersion operation. So, with the dependence of power given by this here. And so, we get because the alpha dependence is already inside pi. Okay, so we get x minus 1 times pi normalized minus over 1 minus x. Okay? You see, I simply use this equation with this instead of k minus k squared. And the k squared also is coming from here, plus the term that I added in front. Okay? So this is a very simple equation. You can replace now this here, replacing k squared by this. And you get L alpha over pi squared in this one and this one to integral x 1 minus x integral 0 1 to y 1 minus y and the log. So this is replaced by this, so this minus x minus y. Okay? This is a nice expression. But to compute it is nice to introduce what we call the main bands of the notation. So this is perhaps something that we know less going on. Because in fact, this logarithm, because we want to compute this integral now. It looks trivial, but it's not in fact, not really. So what we do is use this representation for the logarithm. It is 1 over where I'm doing an integral in the complex plane. Power minus s 1 over s pi over sinus pi s. This is true if C, which is in fact, the real part of S is in the range -1, 0. Now, with this representation, in fact, we will put it inside the integrals, Feynman integrals, and parameter integrals, and it will allow to compute our contribution to the anomaly to all orders easily in the function of the ratio of the masses. So let's do it. So you put it here, and you put the integrals over x and y to the right, and you obtain a n equal to 1 over, I will put alpha over pi squared times 2 over pi pi the integral x is this thing here. Okay, there are x and y dependence, so I will only put the masses now. M squared over m squared power minus s, and then my integral over x integral is equal to x, where I have here x to the power 2, which gives x minus 2s. There is also 1 minus x, and another integral. Yes, and 1 minus s. Don't forget this one. Okay. Yes. So there is a 1 for the first, and here there is minus, which gives plus s. Okay, it comes from this. Okay, the minus s here. Okay, is for everything here. Okay. So, multiply by an integral over y, which looks y times 1 minus s, 1 minus y times 1 minus s. Okay? On these terms and this. Okay, so now this is nothing but the beta function of 1 minus 2s, 2 plus s. This is the beta function of 2 minus s, 2 minus s. And the beta function is written in terms of gamma functions. Okay. This is true for real part of 1 minus 2s positive, as well as real part of 2 plus s positive. And this real part of 2 minus s positive. So these conditions are fulfilled here because we have this. The real part of s is included in minus 1, 0. And it is compatible with this, and this. So no problem to perform the integration, the sub-integration. And we can write the result as alpha over pi squared 1 times the integral in the complex plane. So yes, it's a straight line. Okay, since the real part of S is C, and it's constant, therefore this integration is on a straight line with parallel to the imaginary axis. okay, in the S plane, because the S is complex. Okay. So this gives the following integral: pi power minus S. I replace the beta functions by gamma functions. I do not forget that I have also, yes, I forgot to write it. Okay, this should be here, so I will add it at the end. This is 1 over S, pi over sine pi S. The problem when you do calculations on the blackboard is that it always makes a mistake. It's hard to see to have the same view as when you do it on the paper. Okay, so sorry for this, but anyway, so we got 1 over S pi divided by sine pi S times the gamma function. Divided by, because the definition of the beta function is that you add these two things here, which gives this, and for this case, you simply have 2 minus S squared divided by gamma 4 minus 2S. Okay, which is valid if C is in minus 1, 0. Okay, so from this equation here, we go to this equation. Perhaps that for you it's not so simple because you are more used perhaps to manipulate logarithm than gamma functions. But in fact, there is a very powerful method to do this kind of integrals. Okay. You will see now. We will compute it straightforwardly, and in the next course I will show you the general properties of these integrals. Okay? Just to say that, in fact, you can simplify a bit this result. Okay? Because these are things that you know when you know a bit the gamma functions, but there are formulas for this kind of gammas. For instance, I have the duplication formula, which is the following. Okay, which may be useful, in fact, to simplify here, because I can write 4 minus S as gamma 2 times 2 minus S, and this is therefore 2 minus S, 5 over 2 minus S, 1 over S times 2 minus S minus 1, and also the other, which is the following, I think, this as gamma okay. Now, since there is one numerical and one denominator, you can do some simplifications. This goes with this. Okay, 2 to the power 2 minus s is simplified also. And at the end, you get following integral. Plus infinity s n square minus s 1 over s gamma x 1 minus s plus s divided by gamma 3 minus s gamma 5 minus s times 8, which is 8 2 to the power 4 minus 1 to the power 3, so it's 8. And now you can use another property of the gamma function, which says that x gamma x equal gamma 1 plus x. To simplify again this, and at the end we find the following integral performing a trivial change of variable s becomes minus s. Find again minus yes, this is d. I changed c from d because of this change of variable. S and square over n square power minus, I will put sigma here, okay? Minus sigma, 1 minus sigma over 2 plus sigma and 2 plus 2 sigma times 1 plus 2 sigma multiplied by pi over sine pi s squared. D this time is not anymore in minus 1, 0, but in 0, minus 1 due to this simple change of variable I just did. Now, this equation may be found, for instance, in the paper I wrote with the Raphael. Del B, and a friend of mine who is called Elena. And okay, so we could have stayed with this expression, okay, no problem. I just showed you this expression because it's a bit more simple, because it is the one cited here. It's the same properties, of course, with this in the Riemann family. So now, what we will simply do is have a look to the singular structure of this integral, of the integrand here. Okay? We'll have a closer look. So, if I draw the S plane, the sigma plane. Sorry. I have 0 here, 1, 2, 3, okay. And I see that, for instance, this will give me a singularity at sigma equal to -2. Okay? -2. I have a singularity. But this will give me a singularity at s equal to -3/2. Here. This will give me a singularity at -1/2. This will cancel the singularity at sigma equal to 1. And this gives double poles at all integers, negative and positive. Okay, so I have double pole here. I have a double pole here which is cancelled by the numerator. So not completely cancelled, only one over the pole. I have only one singularity here. Then I have all positive integers after one double pole. And to the left, it's the same. I have double pole here. I have a double pole here, but one more, which means a triple pole. Okay. And here, another one, etc., etc. Okay, so we have the singular structure of our integral, the integral. And we know that we have this straight line where d is between 0 and 1. To perform the integration, it's somewhere here. Okay? So by Cauchy theorem, you can close the integral to the left or to the right. There are conditions for this. Okay? We will not do it today. We will see next time for the conditions and necessities. And for instance, I will compute now the closure of the path to the right. Okay, because it's the simplest one. I have only a simple pole here and only double poles. Here it's a bit more complicated, so I choose to close to the right. Okay. And if I do that, I have to take into consideration so s equal 1 and s equal 2 plus n with n in the positive integers. Okay, these are all singularities I have. So close the path to the right, I have to compute in fact the residues of the subject. Okay? And it's easier to perform by maybe like this. Perform it with the change of variable. S becomes S plus 1. In order to exhibit the singularities that we will encounter here. So if I do that, it's not S, I'm sorry, it's sigma. Okay? Let's write S, okay? This is the sigma in fact, okay? So if I do this, I replace, I find 1 minus S plus 1, which is minus S, divided by 2 plus sigma, 3 plus S, 3 plus 2S, so this will give 5 plus 2S, and 1 plus 2S, which gives 3 plus 2S. So this is for this. And now this, we can do said that pi over sine pi s equals gamma s gamma 1 minus s. Well, it's not obliged to do it like this. And so when I put s equal to s plus 1, I find gamma s plus 1 squared, gamma 1 minus s, which is minus s squared. Okay, so this is, I forgot the term, the mass term, n squared over n squared to the power minus s minus 1. And now I will exhibit the singularity because this is singular at s equal to 0. Okay, I did this change of variable, get the singularity at s equal to 0. So I have to rewrite this as, in fact, using this equation here. I rewrite it as gamma of 1 minus s squared divided by minus s squared. So this allows to extract the singular part of my integral here for s equal to 1. And I finally have cancellation with this s, which is in the denominator. Therefore, I find simply when I keep s equal to 0 to get the residue, since it is 1 over s, so I only have to put 0 here to get the solution. Of course, I extract the singular part, and I get replaced by 0 n squared over n squared minus 1. Here I have the gamma function of 1 times the gamma function of 1, which is 1. And here this number, which is 1.45. Okay, so this result was first obtained with a completely different method by De Raphael and Lavaux. In Phys. Red. So I think it's.
Ah, ça? Est-ce que tu as besoin de la référence dont on vient de parler?
Oui, j'en aurais besoin.
Vous allez chercher les livres.
Mais c'est pas urgent. Okay. Yes. So we got this long time ago.
We have another method.
Okay.
This is more modern way to do things now.
And also, they got only the first term of the expansion. And for them, at this time, it was hard to get the whole things, at least without knowing the exact result. Because at this time of the calculation, this diagram has been computed exactly by Eden, the contribution to the -1 magnitude. In 1966, it was an exact formula that we obtained, and from this formula, you can obtain expansions. Okay. But here we show a method where we get the whole expansion without knowing the exact result. Okay. And then after, of course, knowing the whole expansion, you perform a whole summation, and you get, in fact, the exact result if you want. But the advantage is that if you want only the approximate result, you choose the number of holes that you are testing in, and you stop. You don't compute everything. And if you want to compute everything, you can perform a summation and have the exact result if you want. Okay, so it's more powerful. So at this time, this was known exactly. And I think that when the Raphael computed expansion, it was not easy to get if you don't take the exact result, all the series. But it has been done. It has been done. Now we will compute the subleading corrections. So, the subleading corrections are located here. Okay. So you have to do as before. Perform the change of variable s equals s plus 2 plus n. Yes. So you get for the integral following expression. One minus s minus 2 minus n divided by 2 plus s plus 2 plus n. I will simplify after. 3 plus 2 plus 4 plus 2n. 1 plus 2s plus 4 plus 2n. And square. Okay. Now this contains the singularities. Okay. Everything is alright everywhere. If I take n in n, but here, because here what I have is gamma squared of 1 minus 2 minus 1 minus s minus 1 minus 2. So the singularities are here. But there is a so-called reflection formula. Which says that gamma s minus n equal gamma s plus 1 plus s plus 1 minus s minus 1 to the power n divided by s gamma of n plus 1 minus s. So if you replace this gamma function by this combination of gamma functions squared, you get this, you get n squared over n squared to the power minus s minus 2 minus n 1 over s squared. Okay, this 1 over s squared corresponds to this that I have twice because the gamma is squared here. So 1 over s squared minus 1 minus s minus n minus s minus n over 4 plus s plus n times 7 plus 2s plus 2n times 5 plus 2s plus 2n. This multiplied by gamma squared of minus s gamma squared of 1 plus s. So we see that we have extracted the divergent part. Okay. And now it's not anymore a simple pole. Here we have minus s squared times minus s. Well, 1 over minus s squared times minus s, which gave me a simple pole. Now here we don't have this cancellation. We have a double singularity. Okay? So the residue of this, if I define this as 1 over s squared times the function h of s, this the residue of this expression will be given by the derivative of h with respect to s taken at s equal to 0. Okay? So let's compute this derivative. Tricky to compute this derivative. It's not hard, just that compute. So I will not compute it. I will, because I have to look always at this equation and write here always only write the result, okay, of the derivative of this expression. And h is everything here, but this angular part. So let's compute the derivative of this, define, which is the residue. No, I will define it as, I will avoid this mass dependence which does not depend on S. To the power minus 2 minus n. And my residue is given by square of square times minus n times. Okay, basically what we do is we consider that
to keep that right.
I make the normal plate.
Okay, so what we do basically when we compute the derivative is simply to consider that it is a product of functions. So it's the derivative of the product. Okay, it's easy to compute what we have. The expression we obtain is a bit complicated, and we get the logarithm of the mass times hs. So the logarithm comes from the derivative of this, because this is exponential of minus s log, times, I write everything in an after I will explain, m squared over m squared power minus s times minus 1 m squared over m squared
minus SHS divided by minus 1 minus S minus N plus minus S minus 1 minus N times minus 1 divided by 4 plus S plus N times N squared S squared minus S times HS divided by minus 1 minus S plus 1 over 4 plus S plus N times minus 2 divided by 7 plus S plus N and square of E S minus S as HS divided by minus S times 4 plus S plus N plus okay, moment 7 plus S plus 2N minus 5 plus S plus 2N times N squared minus S H plus minus 1 minus S minus N times 4 plus S plus N times 7 plus 2S plus 2N plus 1 divided by 5 plus 2S plus 2N multiplied by the last bracket. No, not the last. In 1. Square divided by square minus S H S times 4 plus S plus N 7 plus S plus 5 plus S plus 2N multiplied by minus 2 say 1 minus S plus sine 1 plus S and then I close the brackets. So 1, 2, 3, 4, 5, 6, 7. Okay? And I take S equal to 0. So it's integrated, but it's not. It's involved, it's not up. Okay? It's very simple. Just have to become something. So here we have the sine function, and the rest is trivial functions. Okay? The sine function is like gamma function. I already showed you yesterday when we did the expansion of the gamma function. Okay? But here we see that, so it's complicated. You see that we have to perform a summation of this. We have to sum. We have to take S equals 0 everywhere, and then to sum over n from n equals 0 to plus infinity. Okay. So you see that if you have this kind of things, it may be tricky. But when we put S equal to 0 here, you see that side 1 is with minus 2 here, and side 1 is with 2 here. So they cancel. Okay? They cancel it, and you have in fact something which is extremely simple here because everything will let's say 5 of course, and you find I don't write all the intermediate steps. Okay? You find, in fact, this since h of 0 is equal to minus 1 minus n divided by 4 plus n times 7 plus 2n times 5 plus 2n, I can replace it here in this expression, and I find m squared divided by n squared power minus 2 minus n times my logarithm divided by n squared times minus 1 minus n divided by 4 plus n 7 plus 2 times 5 plus n minus 1 over 4 plus n 7 plus 2n 5 plus 2n. In fact, I could have factorized this. Okay. Plus I will factorize times minus 1 minus n divided by 4 plus n plus 2 times minus 1 minus n divided by 7 plus 2n plus 2 minus 1 minus n divided by 5 plus 2n. Yes. Okay. Simply this. Okay. The h, when you replace it, there are lots of cancellation. H is here, is here, is here, is here. Okay. Everything cancels, and in fact here also, because you can put everything in the same denominator, and you get this result. Minus 2 minus n times my logarithm times 1 plus n divided by 4 plus n 7 plus 2n 5 plus 2n plus following thing n cubed plus 2n squared plus 8 n minus 9 divided by 4 plus n 7 plus 2n 5 plus 2n squared. Okay? This result has been obtained with this method in the paper I cited Islet, okay, already. And otherwise, it has been obtained directly from the exact result of element, remember, in the reference that I have put now. So it is known one. And another that has been more recently will also be cited. I will do it after. This is yes, this is something very well known. Edison than well. And this is UCD CNO. Report 1968. In fact, I didn't see this reference. You can find it, or it's not so easy. And it's cited by Laporta et Vanidi as where an exact formula in the ratio of masses is contained, but we don't know if it is exact and expanded, or if it is exact without expansion. Expressed in terms of logarithms and logarithms. I don't know what. Okay, so I'm not sure that it is contained here, but it is contained in another paper. So we checked our results that we obtained with this method in the paper by Lee and Sandberg. And there is an error also, QED, but 48, 1993, okay? And these two physicists, they obtained the result that I quote here by from the exact result of Eland. We obtained it from the exact result of Eland that I cited a few minutes ago.
Professor Revidi, the guy from Bologna, he did a lot of higher order calculations, and up to 4 loops.
Yes, but he's the guy who did the 3 loops.
3 loops, no?
Yes. Well, he did also 4 loops, but not the whole thing, because the whole thing is not known analytically. But
4 loops analytically is not
yes, he finished to compute the 3 loop in 1996. And he did most of the calculation, not all, of course, but yes, lots of work here on this. Well, I thought, so this is the 2 loop result. Okay? You have an exact dependence, because you will now perform the summation. If you do the summation, you can express these sums in terms of special functions, no problem. You perform analytic continuation, and you get, because this is a series that converge only when n, big N is less than small n. Okay. Sigma will converge when n is less than n. Okay? Which means that, for instance, for the muon here, so big M was excited. So this is an electron. No, I'm sorry. There is minus sign. Okay? There is minus sign. This is the converse, I'm sorry. And this is the tau. Okay? Imagine you want to compute it with an electron here. Either you do the summation of the series here. Okay, you do the same. If you want only one term, it will be very simple. In 10 seconds you have the answer. Okay? But you also can perform the resummation of this, write it in terms of special functions, and perform analytic continuations of with these special functions. Okay? Because this series will not converge for the electron. Okay? But once you have expressed the series in terms of special functions by analytic continuation, you have the right to use the mass of the electron instead instead of the mass of the tau. So you choose the way you want to compute it. Okay?
Also, since you know the literature in Yale, I'm asking, in the 70s, and also back to the beginning of 2000, 2005, in the 70s, people from Imperial College, Del Burgo, Capper, these people, they calculated, not this, they calculate quantum gravity corrections to QED processes, like even for the beta function. Do you know whether in the literature anyone considered quantum gravity corrections with the G-2 factor? Maybe they are very small, but do you know by chance?
I don't know.
You don't know. So this means that nobody did. In the literature, it didn't come to you, remember? You never found this in the literature.
Well, no, but perhaps it must exist.
No, but the Raphael would have told you probably. Because I'm asking, because in the beginning of the 2000s, Wilczek did some works. And he was trying to claim that the beta function of QED could become negative. QED could exist as a thought of freedom if you consider quantum gravity.
Okay, that's interesting, yes.
But I think that work, at least from what I know in literature, it came out to be wrong. Okay, so that was a wrong claim. But anyhow, people have always considered quantum gravity corrections the QED process. So my question is whether for the G-2.
I have no answer, I'm sorry, but
I see.
it's interesting.
Because people in the Imperial College, Salam's group in the 70s, they calculated quantum gravity corrections to the vacuum polarization. They found some interesting results, but not for the G-2. I
will try to.
If you find anything, let us know. Just for the sake of our culture.
Yes, and for mine.
Because anyhow, quantum gravity is physics beyond the standard world, and also it will be interesting. Okay.
Thank you for this super gravity.
Gravity or super gravity?
So we spoke about QED. We did a lot of work in computing in QED the three-loop contributions to G-2. And I said that in 1996, the calculations of three-loop contributions were finished. And that's right. And they finished, in fact, it was not the mass-dependent contribution that we will see now, but we finished, and after the mass contribution that we will show now, which is the only diagram that we can at the three-loop level compute together, and we will not be able to finish it. We have to do a bit of work. It's the same class. Okay? Simply this one. Okay? And when you have L here, L prime here, and L here, this is the last diagram of QED that has been computed at 3 loops. It has been computed 1997, I think, by example. And another guy, and I don't remember the reference. Okay. And what is interesting with this diagram is that it appears in, well, if you consider all possibilities for the Deltons here, is that it appears in all contributions of QED as this, all the classes of contributions of QED. I showed you, remember, A1, A2 of ML over ML prime, A2, A3 over ML over ML7, and A4 ML over ML prime, ML over ML7. Okay? Because for this contribution,
you put the same lectern everywhere. For this contribution, you put the same lecterns here, different from this one. For this, the other, okay, you put electrons here for this one, for instance, 1000 for this one, for the other. And this is simply when we have this case. Okay, so Laporta and LND finished the whole calculation in 1996 of, I forgot, of this. Okay. Then this one was completed just 1 year after, or I don't know, with all dependencies. So it is interesting also because it depends on mass ratios. Okay? So we will not have only one sum, we will have double sums. Okay? And so it is interesting to try to compute it, to see how things generalize for the main bounds of representation in the two-dimensional case. Okay? So this is what I propose to do. At least now I will show you that we can have a simple parametric representation of the contribution to this diagram to the anomalous magnetic moment. And then next time we will do some calculations, not all because it's really much heavier than what we did. But at least it will give you a good idea. Nice to know how things go from one dimension to two dimension to the maybe thousand rotation. Okay, so as in the two-loop case, we will replace in our one-loop calculation in vice figure the free photon propagator by this one. Okay? And this is a bit more complicated than what we did, but it's maybe platform. Okay, this means that if you consider this, I will call you this, plus I don't quite hear the exact dependence of the gauge term, but I show that you have to check at least. So this is the free propagator here. It will be replaced by minus ij mu divided by k square plus a k u no, yes, so it's sigma times what the polarization. We showed that it can be written as k sigma k tau minus J sigma tau times k squared pi normalized 1, because now there are 2 of k squared, times the propagator here, which is the same form as this one, so minus my index is tau what I chose alpha over k squared plus k tau alpha divided by k squared. Okay, you have the second polarization, which is times I k alpha k beta is beta minus j alpha beta times by 2 is like r k square times the last propagator minus I j beta u divided by k square plus a k beta k u divided by f k square. Okay? So now, using the fact that j mu beta equal delta mu beta, you can show in fact that there will be only one term that will contribute in this, because you have two terms, and only one, the one given by the j mu, will stay at the end, because all the other